Thinking about quantum gravity. Chapter 1c, the peculiar nature of quantum non-locality. Let us start by defining locality. If an event takes place at a point A in space at a time ta, it can influence a later event happening at point B at time tb only if the event B is on or inside the light cone of A. That is, suppose a light signal were to be sent to point B from A at the instant when A happens. Then event B can be influenced by event A only if B does not take place before the light signal arrives at B. Also, it is assumed that for B to be influenced by A, something travels through space from A to B. For instance, the traveling aspect could be a wave, it could be an electromagnetic wave or a sound wave. There is no action at a distance. We expect something to be transmitted if B has to be influenced by A. This something cannot travel faster than light, that is, the laws of special relativity are obeyed. And locality holds in the classical world. Let's look at an example. Suppose an experimentalist A on the Earth sends a laser beam to a point B on the Moon. At some time when the beam is on its way, an explosion takes place at point B. This explosion could have been caused or influenced by the laser beam only if it takes place after the beam arrives at the point B. If the beam is still on its way and the explosion happens, then clearly the explosion is not due to the beam. That is the meaning of locality. In the classical world, there is also what we call local realism. Realism means that an object has pre-given properties like mass or size, etc. And these properties are not changed by making a measurement on the object. This is what classical bodies are like. Let's look at an example. Suppose on the Earth, the experimentalist A, let's call her Asha, is going to make a measurement along with the experimentalist B, let's call him Babu, who's on the Moon. In between the Earth and the Moon, there's a space station X, which simultaneously sends out two rockets, one to Asha at A on the Earth and the other to Babu at B on the Moon. Each rocket is carrying a ball. The balls are identical except for these two differences. One of them has a mass of 100 grams, the other has a mass of 99 grams. The first one has a diameter of 10 centimeters. The second one has a diameter of 9 centimeters. Both Asha and Babu know both these balls have these properties. So these numbers are known to both of them. They also know that one ball is coming to Asha and one ball is going to Babu. What they do not know is which ball is going to whom. So clearly when the balls arrive, they make a measurement. And suppose Asha finds out that her ball is 100 grams, she obviously concludes that the ball that's going to Babu has a mass of 99 grams. This knowledge does not mean that any influence traveled from A to B. Of course not, because the ball B has these classical properties irrespective of what's happening at A. So that is realism, that just the knowledge that Asha has that her ball is 100 grams does not imply that something was transmitted to make ball B 99 grams. That's an intrinsic property of the ball. Quantum systems violate such locality. Quantum systems violate local realism, as we'll see. Quantum correlations are non-local. There is an influence outside the light cone. It is not a causal influence. It's not cause and effect. It is not that something travels from one place to the other to make this effect happen. So there's no superluminal signaling, but there is an influence nonetheless in the sense that we just see. We'll also find out, just with some introspection, that quantum non-locality is an inevitable consequence of the superposition principle and the collapse of the wave function during a quantum measurement. So the key to quantum non-locality is the breakdown of superposition when the wave function collapses during a measurement. Okay, let's look at quantum non-locality a little more closely. Again, we have our experimentalist Asha on the Earth, Babu on the Moon. This time the space station does not send out two classical balls. It sends out two quantum particles which are prepared in a singlet state. An electron and a positron are created from a spin zero particle at the space station X, and it's so arranged that the electron flies off to Asha on the Earth and the positron flies off to Babu on the Moon. The net spin of the electron and positron must be zero. So electron has spin pointing in some arbitrary direction, and the positron spin would point in exactly the opposite direction to the spin of that of the electron. The electron spin is going to be measured at the Earth. The positron spin is going to be measured at the Moon. Okay, so we will arrange things in such a way. The measurement B takes place outside the light cone of A. Say A makes a measurement. At that moment, A sends out a light beam to B on the Moon, and the measurement at Moon is so timed that it is done before this light beam arrives there. So the two measurements are space-like separated. And as we'll see in a moment, one of the measurements influences the other measurement non-locally, and it's important to note that in such a situation when the two events are space-like separated, it is not possible to say that A influenced B. It's also possible that B influenced A, just depends on which inertial frame you are in. As you know, if two events are space-like separated, they do not have a specific or well-defined time ordering. There's no cause and effect possible between space-like separated events. So suppose A happens before B in some inertial frame, you can go to another inertial frame moving with respect to the first one in such a way that in the second frame B happens before A. Okay, this is the experimental setup. Both Asha and Babu are going to measure the spin of the electron or the positron along one of two possible directions which they can choose randomly, say using a random number generator. The spin will be measured either along the z-axis or along the x-axis by both Asha and Babu. Now let's see what happens. Suppose Asha makes a measurement of the spin along the z-axis and finds the result plus z. What does that mean for the spin of the positron? You can make a picture like this. The electron is initially in some state which can be written as a superposition of two states, which is the state 1 is spin pointing along plus z, state 2 is spin pointing along minus z. When Asha makes a measurement on the electron spin, it collapses to plus z. So the superposition is being broken, and that's important for us to note. The wave function of the electron spin collapses to plus z. And because the electron and positron together preserve spin, the total spin angular momentum has to be zero. The instant that the electron collapses to plus z, at the same instant, instantaneously, the positron collapses to minus z. And after that, suppose Babu is going to make a measurement. If he decides to measure along z, he'll definitely detect minus z. But if he's going to make a measurement along x, he might get plus x or he might get minus x. And if you repeat this experiment with a very large number of pairs of electron and positron, that is, you find out the statistical outcomes. Then when Babu, if he's always going to measure spin along x, and if all the electrons are along minus z, half of them will come along plus x and half of them will come along minus x. What is important for us to note is that there is a non-local influence which is a consequence of collapse of the wave function and the total spin being zero. And we recall that collapse of the wave function is the same thing as the absence of macroscopic superpositions. So it is the absence of macroscopic superpositions which is responsible for quantum non-locality. For example, suppose there were macroscopic superpositions possible, and the pointer that Asha is using can be in both the states plus z and minus z at the same time, then obviously there is no collapse of the electron wave function. It will remain in a superposition and there will be no non-local influence. The positron also will remain in a superposition. Just to continue with a slightly different example, now suppose Asha measures the spin along x and finds the result minus x. Then again, instantaneously, the spin of the positron will collapse to plus x. And if Babu measures along the x-axis, the result would definitely be plus x. And if Babu measures along the z-axis, the result will sometimes be plus z and sometimes be minus z. So this then is the essence of quantum non-locality. Collapse of the wave function enforces on us that there be instantaneous influence outside the light cone, simply because there is a quantum correlation between the electron and the positron. And of course the physics is more general, it's more generic to quantum mechanics, not just spin. Spin is something we just used as an example. When this became clear, of course it became clear in the early days of quantum theory that this is how the physics of quantum physics is. There is non-locality. It certainly perturbed Einstein, and in 1935, EPR, Einstein, Podolsky and Rosen wrote a famous paper which generally is referred to as the EPR Paradox. So let us see what is the paradox, what is their discomfort. So the same setup, the electron and the positron in a singlet spin zero state, electron going to the left, positron going to the right. So what are the two important aspects? Let's recall. One is the collapse of the wave function, and the other is quantum non-locality, which is an influence outside the light cone. To Einstein, to EPR, locality is sacred. That is not something that they would like to give up. And then that led them to conclude that there is some problem with quantum mechanics. Let's try to understand their argument. So this is how it works. If there is collapse of the wave function, there is non-locality. So if you want locality, you will have to get rid of the collapse of the wave function somehow. We'll see how they did it. So in other words, suppose you want to retain collapse and yet have locality. That gives rise to a contradiction, which is the EPR paradox essentially, and let's see how that comes about. Let's remember, we are retaining collapse, but we are giving up non-locality. We insist on locality. Suppose Asha had made a measurement of the spin along the z-axis and found the result plus z. It implies that the positron must have had the spin minus z. Now remember, there is no non-local influence. There is no influence allowed. We are insisting on locality. So the positron cannot be affected by whatever measurement Asha makes. So if Asha had measured along z, the positron would have been in the state minus z if Asha got the result plus z. Now, on the other hand, if Asha had measured spin along x and found, say, minus x, it means the positron spin must have been plus x. Now, see what's happening on the right hand side. The positron is not being influenced by the electron because of locality, and yet in order to produce the result minus z as well as the result plus x, it must be already possessing a definite spin along the x-axis and a definite spin along the z-axis. That is the only way these two results can come about in the absence of non-locality if we insist on locality. So, in order to be able to explain results of experiments that could have been done, measurements that could have been made, the positron has a definite spin both along the x direction and along the z direction. That's impossible in quantum mechanics because spin along the x-axis and spin along the z-axis, these two are non-commuting observables. They cannot have simultaneous eigenvalues. It's impossible for the electron or the positron to be both in a definite state of both z as well as x. So that is the contradiction. That's the paradox that EPR point out, that either you can have non-locality and then fine, you sort of break special relativity, but you can then live with quantum mechanics. But as EPR would desire, if you insist on locality, you cannot have collapse of the wave function, and then the state which the positron is forced into is impossible in quantum mechanics. How to get out of this? EPR's suggestion was that they would like to retain locality, hence quantum mechanics is incomplete. What that means is the following. We saw collapse and locality cannot coexist. There's a problem with that in QM. There's a contradiction. So they said, let's get rid of collapse. If we retain locality, let's get rid of collapse in the following way. So see, what is collapse doing? It is breaking superposition. Suppose I'm measuring spin along the z direction, and initially the electron is in superposition of plus z and minus z states, and sometimes I get z, sometimes I get minus z when you make measurement with successive electrons. What collapse does is break superposition, and that doesn't work with locality. So what if there is no collapse? What if the initial state of the electron is either plus z or minus z, and yet you have to retain the randomness of the outcomes? So EPR bring in what we call nowadays hidden variables. As the state of the electron, or the positron for that matter, is not described just by the wave function of the electron or positron. That information is incomplete. There is some additional initial values for this so-called hidden variables, which are randomly assigned, which result in the following, that the electron by itself is not in a superposition of plus z and minus z. It can either be in such a hidden variable specification which allows the state to be plus z, or it allows the state to be minus z. The hidden variable is randomly assigned in such a way that the state is either plus z or minus z. And when we make a measurement, it will sometimes come out plus z or minus z. Statistically, the system of measurements agrees with that of quantum mechanics. It's just that individual objects already have a predetermined state. So this really makes the electron quite like the ball that we have been talking about. Local realism is reintroduced. EPR bring back local realism at the expense of adding randomness. That randomness in the initial values of the hidden variables is needed because you have to explain the random outcomes of the quantum mechanical measurement processes. So what have we done? We have given up on non-locality. We have given up on collapse of the wave function. Instead, we insist on locality. EPR insists on locality and on additional hidden variables which bring in local realism, which bring in realism along with randomness, which is added through these hidden variables. So quantum mechanics is made complete by adding hidden variables. So this is now what we call a local hidden variable theory. So EPR said in summary that because locality is a sort of sacrosanct assumption, that's how special relativity tells us the world is like, quantum mechanics is incomplete and additional variables must be brought in to be able to explain what is happening if locality and realism are to be preserved. So thus, when hidden variables have been brought in, let's see what is the story for the positron now. The electron is in a definite state. It is no longer in a superposition, it's in a definite state, which is a real, local realistic state with a definite value of spin, which does not change, by the way, when you make a measurement. That's what's meant by giving up on collapse. Whatever was the value or the direction of the spin before measurement, the same will be after measurement. And the random hidden variables are so assigned by nature itself that the electron and positron spin continue to be correlated. If the electron now has a definite spin in some direction, the random variables are so arranged that the positron has a spin in the opposite direction. So there is a set of hidden variables which now allow the positron to be in the state minus z, and which also allow the positron to be in the state plus x. That's how the random variables are assumed to work. Now, because there is realism, the spin in the x direction and the spin in the z direction obviously commute with each other because the state is known exactly, and hence the contradiction that arose in QM when we dropped non-locality and when we retained collapse, there was a problem. And so what we did, we retained locality, we also then dropped collapse, we brought in realism, we brought in hidden variables, and then there is no contradiction anymore. So what do we have? On the one hand, we have local hidden variable theories, which are local realistic theories, and on the other hand we have quantum non-locality. So which is correct? How do I know now? What am I supposed to do to find out what's happening, and if the results of experiments can be explained both via quantum non-locality as well as by hidden variable theories? So how to tell the difference? That is where comes in the great work, one of the most beautiful and important pieces of work in theoretical physics, Bell's theorem, 1964, which helps us decide between non-locality on the one hand and local realism on the other. So as we saw, EPR proposed that quantum mechanics should be modified to have additional degrees of freedom, which makes these so-called local hidden variable theories. What Bell showed that the essence of the theorem is that Asha and Babu can perform measurements on correlated systems whose statistical outcomes of these repeated measurements, they will agree either with local hidden variable theories or they will agree with quantum mechanics, but they will not agree with both. So this concern that we had, how to experimentally tell whether QM is right or whether local hidden variable theories are right, Bell showed that you can in principle set up measurements which whose outcomes will be such that they can be explained either by local hidden variable theories or by quantum mechanics, but not with both. So we can now do an experiment of the Asha and Babu correlated measurements type. As I'm sure you well know, these experiments have been done many times, and every time they have confirmed quantum mechanics and non-locality, and they rule out local hidden variable theories. In other words, there are results of experiments which can only be explained by assuming that quantum non-locality is very much at work. It is there. It's a property of nature, and you cannot explain away these experiments by local realism. Local realism is out. And in this one instance, well, one can say that Einstein was actually wrong. The so-called spooky action at a distance is not spooky, it's there. It is in a sense action at a distance, and it is there. Okay, so we say quantum non-locality is for real, it's there in nature. There is an influence outside the light cone. This influence is, by the way, not causal because it can be shown as we see in the next slide. Information cannot be sent through such so-called Bell correlations or EPR correlations. So the effect is not causal. It's not cause and effect kind of thing, but there is an influence. There is something happening outside the light cone of A, which is different from nothing happening, so to say. So that brings us to this question, which has been there for a long time. Does quantum non-locality violate special relativity? Now we could ask, would EPR have written their paper if they thought special relativity is not violated by quantum non-locality? Clearly, to Einstein, I think it was quite obvious that special relativity is in trouble if quantum non-locality is correct. And one could actually ask this interesting question that how would Einstein have reacted if he was there to see Bell's theorem and if he was there to see that experiments actually confirmed quantum non-locality? This one can ponder over. Okay, so we continue with this question. Does non-locality violate special relativity? As we said, quantum non-locality cannot be used to send information faster than light. In one way, that's easy to see. Suppose Asha measures the spin of the electron, say along z direction, finds the result plus z. If this information has to be communicated to Babu, that has to be done by conventional means, say by sending a light beam. This information cannot be sent faster than light. So, quantum non-locality does not permit superluminal signaling. Faster than light signaling is not allowed, even though there is an influence outside the light cone. This condition is known usually as microcausality, namely commutators of fields in quantum field theory vanish outside the light cone. That is the microcausality condition, namely quantum non-locality cannot be used in a cause and effect sense to transmit information faster than light. Thus, we say quantum theory is non-local, yet it is microcausal. That's quite profound. You can do something outside the light cone, but you cannot use that to send information faster than light. So it looks as if there's an instantaneous transmission from the electron to the positron, but we have to understand better what really that means, and we come to that in a moment. We should also note something interesting, that the collapse of the wave function, which is what caused non-locality in the first place, collapse is a nonlinear process, and such a nonlinearity would generally lead to superluminal signaling. That's known in theoretical physics. Nonlinear violations, nonlinear modifications of the Schrödinger equation result generally in superluminal signaling, except when the collapse which induced this nonlinearity obeys the probability rule, which is the Born rule. This is really remarkable. It's saying that if the collapse obeyed probability rule, which is other than Born rule, then the nonlinearity introduced by collapse would lead to superluminal signaling and violate microcausality. So this is deep. One should try to figure out, understand what is the connection between the Born probability rule, microcausality, and quantum non-locality. There's clearly a delicate balance which sort of allows quantum theory to hold on to special relativity, yet there are issues which need understanding, which we come to now. Okay, so as we have said again and again, there is a non-causal instantaneous influence outside the light cone. Now, this is to be looked at in the following way. We have our two experimentalists, Asha on the Earth, Babu on the Moon. But it doesn't have to be Earth and Moon. These can be two galaxies which are separated by billions of light years. Asha is in the Milky Way, let's say on the Earth, and Babu is on some planet in a galaxy, yet in a star around some distant galaxy, a billion light years away from the Earth. And we can still repeat the same experiment at that enormous distance too. A measurement on the electron will instantaneously cause collapse of the wave function of the far away positron, as if the system were oblivious to distance. This quantum system, in which the two entities, the electron and the positron, are separated by a billion light years, don't care for that distance. You make a change here to the electron, it's instantaneously felt a billion light years away. So what does that mean? What does that tell us? I think it's telling us something very profound which we cannot ignore. Distance does not matter to quantum systems. In a way that should be evident to us, quantum states live in the Hilbert space and evolve with time. There is no distance. The physical distance, the way we understand quantum theory, is not there in the Hilbert space. But on the other hand, the particles that this state is describing, they live in physical space. The electron, the so-called particle, is in 3 space. The positron is in 3 space. Yet the state constituted by this electron and positron doesn't care for distance. This is actually a strong indicator that the light cone is irrelevant for this quantum process. You do something to the electron, it instantaneously affects the positron outside the light cone. So it means the light cone is not playing any role. If it was playing a role, then we should respect special relativity. So the light cone is irrelevant to quantum processes like this. Namely, collapse of the wave function has nothing to do with the light cone structure of space-time. I think that's quite obvious. That's why quantum non-locality is there. Hence, we should be able to describe this process, this collapse and quantum non-locality. We should be able to describe it without referring to the space-time of relativity. So, I'm not saying that quantum non-locality violates special relativity. What I'm saying is quantum non-locality should be described without any reference to the light cone or to space-time. In other words, collapse should be described without any space being brought in. And let's remember that collapse of the wave function is the same thing as the absence of macroscopic superpositions. So it is the absence of macroscopic superpositions which is responsible for quantum non-locality, and quantum non-locality is suggesting to us that there should be a description of quantum theory in which there is no reference to space-time. Why? Because there is a quantum influence outside the light cone. So we should have a description of quantum theory, and in particular of collapse of the wave function, a description in which the light cone locality-based structure of special relativity is not there. So absence of macroscopic superpositions which cause non-locality, that's a question in quantum foundations. It's telling us to revise our notions of space-time structure insofar as quantum theory is concerned. We need to look at space-time differently. I think that's what non-locality is telling us. So, and if we have to change the structure of space-time in quantum theory, of course, now then we are dealing with quantum gravity. So, we are beginning to see how issues that are important to quantum foundations are deeply connected to issues that concern quantum gravity. We have seen this picture before, so I've added a new bit on the lower hand side. On the left hand side, we have, in the micro world, we have quantum systems which obey non-locality. On the right hand side, we have classical systems where locality holds, local realism holds. And you can see now, again, we are in a conflict zone. What's going to happen in the Meso-world in the middle? You come from the left hand side to larger and larger, less quantum systems. but still non-local. You come from the right hand side to the left where locality holds, but you make these systems smaller and smaller. The only way we can make peace with the Meso-world if locality is actually an approximate property of the universe. So, but this is to me very strong evidence that space-time in quantum theory cannot fundamentally be the space-time of special relativity. We use special relativity in quantum theory. It works, but there are situations where it leads to puzzling picture of the universe that, as we just saw, quantum non-locality does not quite sit well with special relativity. It's telling us that please describe quantum processes without referring to special relativity in any way. So if that is how it is there to be, then it's obvious that special relativity, we can call it classical special relativity, is an approximate property of the universe which probably works well so long as the universe is classical, but it's not the way to deal with space-time fundamentally in quantum theory. This is suggested also in this cartoon, which will link us to the next lecture and which we'll have a lot of time to talk about in the coming lectures. There is in the upper plane what I call level 3 classical dynamics, level 2 on the lower plane what I call quantum theory on a classical space-time. So level 3 is quite clean. It's the world of Newtonian mechanics and special relativity. Matter bodies are classical, matter fields are classical, that's classical mechanics or classical dynamics, and space-time is also classical. CST stands for classical space-time. So this, there's balance, there's harmony. Matter fields are classical, space-time is also classical. On the other hand, at level 2 in quantum theory, we are actually breaking this harmony. We want to stick to a classical space-time CST at level 2, but now matter has become quantum. We will make a case in the next lecture and the lectures after that, that this is an approximation to ask quantum theory to coexist with a classical space-time, namely Minkowski space-time as shown here. This is an approximation which runs into trouble in certain situations, and I think the conflict or the tension between quantum non-locality and the light cone structure of Minkowski space-time is one example of this disharmony at level 2. And later on we'll also argue that actually at level 2 we should not be really working with this classical Minkowski space-time. We'll have something that we call a quantum Minkowski space-time or quantum space-time, and we'll argue that classical space-time as in level 3, space, we will argue, in fact comes from collapse of the wave function. Collapse of the wave function is what localizes bodies and gives rise to space as that which is between classical bodies. So if space comes from collapse, then indeed we will have difficulty if we are trying to describe or understand collapse from the vantage point of classical space-time. You see what I'm saying? Space comes from collapse, then I better try to describe collapse in a way which does not involve physical space. So this problem of quantum non-locality that we are seeing possibly very likely comes about because we are assuming classical space to exist, whereas classical space in fact emerges from collapse of the wave function. So a good explanation of collapse of the wave function would be or should be without classical space-time, and then the problem of non-locality, the puzzle of non-locality and its conflict with special relativity simply does not arise. The light cone structure is gone if you describe collapse from a point of view of a quantum space in which classical physical space is not there. there's no question then of non-locality. In fact, there's no question of distance. The whole trouble of non-locality came about because we said the positron is a billion light years away from the electron. How come instantaneous influence is then possible? What we have to get over with is the following. The electron and the positron together, we will argue, live in a space, in a different space, not physical space, live in a quantum state really, in which there is no notion of distance. So it's meaningless to say that the positron is a billion light years away from the electron. No, both of them just are. You see, they are just are in that quantum space. There's no notion of distance. If there's no notion of distance, there's no notion of instantaneous transmission or a very long distance spooky kind of action. There's no distance, so there's nothing spooky. So we'll talk more about this next time. We'll talk about the problem of time in quantum theory. So thank you for listening to me, and I'll see you next time. Bye.